Good afternoon, everyone. Welcome to Australian Tsunami Warnings and Hazards webinar. For those joining us for the first time, welcome. And for anyone who's joined us for our webinars before, welcome back. To celebrate National Science Week, today we will be giving you an in-depth look at what causes a tsunami and how we monitor for possible tsunamis and what warning information is issued when we do. My name is Jordan and I will be your moderator today. I'm joined by Claire, who will be producing today's webinar, and together we will help make the webinar as interactive as possible. Before we start, may I ask for your attention as we cover off some housekeeping items. With the current situation as it is in Australia, this webinar will be conducted from our respective homes, which you've probably already guessed. Please bear that in mind as we may encounter some technical issues during the broadcast. Our broadcast today will run for 60 minutes with plenty of time allocated for questions. The webinar is also being recorded and the video will be shared with you via email. For first-time webinar attendees, please see some helpful tips on your screen now. Most importantly, please see the chat box where you can send through any questions or feedback for the presenters. Now, please use this box and not the Q&A box to send your questions to us during the session, and we will answer as many as possible during the allocated breaks. Now, it's the little speech bubble button in your taskbar on the screen. The icon will turn blue once it's on, and that's how you know. If you want to test out if the chat box is working for you, please feel free to tell us your name and where you're dialing in from. We always love to know where our attendees are coming from today. So in response to feedback received from previous webinars, here is some information on how to participate in our polls. When a poll is in motion, you'll see a set of questions on the right of your webinar screen. Please select your answer choice followed by the submit button below them. I'll also take this moment to thank those of you who sent in questions during your registration process. We have developed the content of this session in accordance with the common themes of those questions, so thank you for engaging with us. And finally, I'm delighted to introduce you to our presenter, Dr. Diana Greenslay. Diana is a principal research scientist with the Bureau of Meteorology's research program. She has been with the Bureau for over 20 years, working on research and development of marine forecast systems, including waves, storm surges, tsunamis, and other coastal hazards. Welcome, Diana.
Hi, Jordan. Thank you very much. Good afternoon, everyone.
Good to see you're happy and safe at home. Would you like to tell us what we're going to be hearing about today?
Sure. Okay, so here's an overview of what I'll be talking about. We'll start off with some basics, look at the definition of a tsunami and where the word comes from. Then we'll look at tsunami hazard for Australia, so both what has happened and what we might expect to happen in the future. Then we'll look at how we observe tsunamis and the particular instrumentation that we use. And then finally, I'll give an overview of the particular tsunami warnings that we issue and what we issue and how we determine that threat level.
Excellent. Plenty to learn from today. And sorry for everyone who was getting a huge amount of sunlight that was coming in over my shoulder. Into our talk proper, we do want to start off with a poll. So the question is, when was the last time Australia issued a tsunami warning? Now, was it A, 2004, B, 2011, C, 2016, and D, 2019? While you get your answers in, we've got a couple of questions. So speaking of 2004, which is A, I think it's the main reason why most people are fearful of tsunamis. I mean, in Australia, I know that tsunamis really became front of mind after the big 2004 Boxing Day tsunami. John has asked, why was the tsunami on the 26th of December 2004 so destructive to countries such as Indonesia and even Somalia, but so negligible in its impact to Australia?
Yeah, so that's a good question. I wouldn't say it was negligible. There were maybe a few small impacts, which we'll see a little bit later. And I will be showing an animation of that tsunami so that you can actually see the impact. So I guess the key reason why we didn't have much of an impact in Australia is firstly, we were a long way away from the earthquake, and also the orientation of that earthquake. So most of the energy was directed across the Indian Ocean towards Africa, and of course, obviously towards Indonesia behind it, and less of it came around towards Australia. So it's a combination of distance from the earthquake and orientation.
Okay. Denton has asked, when we receive a tsunami warning on water, what is the first thing we should do in a 6.2 meter fishing vessel. That's very, very specific. I'm assuming that
It
Denton
is.
has a 6.2 meter fishing vessel.
Yes. It is very specific. I personally don't have a fishing vessel myself, and to be honest, I'm not sure that it really depends on how big your fishing vessel is. So look, it really depends where you are. So I'll talk a little bit later on the amount of warning that you'll get. And so if you're on the water in whatever vessel, you should first figure out if you've got time to get to shore based on when we're forecasting when that tsunami has arrived. So if you think you've got time to get to shore, then you should take your boat in, tie it up securely, and then remove yourself from the foreshore so that you're in a safe area. If you don't think you've got time to get back into a port or harbour, then you should probably go out to deep water, or just go out as deep as you can, because we'll see that there's a lot less impact if you're in deeper water.
Okay. And again, more of that will be coming up. We do have a couple of questions that people have asked us now. Just to clarify with the poll, where issued tsunami warning happen on land. Okay, so that's meant to be the parameters in which you answer that poll question. We do have another question that's come from Patricia. Now, I've seen this in the movies as well, and I kind of assumed that maybe we had them here in Australia. Do any coastal communities have audible warning systems in towns that are like linked to the bombs warnings or something, like a big siren?
Yeah, a good question. As far as I know, I don't think we do. One of the reasons for that is generally we can actually issue a warning with enough time, so we don't really need to alert people actually at the beaches. So as far as I know, I don't think we have warnings. We don't have sirens actually on the coast.
Okay, and I thought this might be a really interesting one to ask you, because you are an expert in this field. Natasha wants to know, how did you get into this field, or how does someone get into this field? What are the qualifications required? She's studying a Bachelor of Environmental Science or Environmental or Geosciences, so she'd love any assistance would be appreciated.
Okay, well, so that's a good start. So I actually did maths at uni, and I did maths just because I was good at it and I liked it. And when I started working at the Bureau, yes, oh so long ago, 20 years ago, I actually started working in wind waves, because we didn't really do much in tsunamis then. It was only when the 2004 tsunami happened that then the Bureau and Geoscience Australia were tasked with doing tsunami warnings. And we didn't have much expertise in tsunamis at the moment, but they said, Diana, you do waves, you can do tsunamis now. So then I moved into tsunamis. So I guess depending on what area you'd be interested in getting into, both the Bureau and Geoscience Australia, which is our partner in the Joint Australian Tsunami Warning System, have Warning Centre. They both have graduate programs, so you should definitely look at our web pages to look into those. So as a bureau, you would come in potentially as a forecaster, and as part of that job, as part of that role, you would be doing tsunami warnings. And Geoscience Australia have a graduate program. I think it's something similar, but you do more project work. If you wanted to go into the research side, then you should probably look at maybe doing some postgraduate research work. There's a number of universities around Australia that specialise in coastal hazards. So send us an email afterwards, and I could potentially put you in touch with some people.
Okay, great. Yeah, well, the email were the questions at bom.gov.au, Natasha. That's where you can contact us. Okay, so we have the results of our first poll, and we actually have a tie. Most people believe it's either C or D, 2016 or 2019. Diana, what's the answer?
Okay, well, in chronological order, I'll go through them. So 2004 is not the answer. So that was the Boxing Day event in Indian Ocean, but we did not issue a tsunami warning, predominantly because we didn't actually have a robust tsunami warning system in place then. 2011, that was that's essentially a reference to the big Japanese event in March 2011. We didn't issue a warning then because we had a warning system in place, but we assessed that we didn't need to, there was no threat to Australia. So we issued a no threat, that doesn't count as a warning, and we think that was the right thing to do. 2016 is the correct answer. So in 2016, there was a tsunami warning issued for Australia. That was actually a fairly large earthquake. It was magnitude 7.8, 7.9 in the middle of the Indian Ocean. And you'll see, and we issued a warning for our offshore territories, Cocos Island and Christmas Island. That was actually once after a little bit of time, the magnitude of the earthquake was reassessed and reduced, and we lifted those warnings. But that was actually the last time we issued a warning. 2019, there was no warning then. That was just a fake. So 2016 is the answer.
Excellent. Well done to everybody who got that right, and thank you for your answers. Our poll, we'll have another one a little bit later on, but more importantly, you've seen how well Diana answers questions, and there is plenty more time for her to get to some of yours. So please start sending them in the chat box now, and we'll have a dedicated question and answer time a little bit later on. Diana, take it away.
All right, thanks, Jordan. Okay, so starting off, what is a tsunami? So you probably know the word tsunami comes from the Japanese word tsunami. What you may not know is it's actually composed of these two kanjis. Actually, let me just check. I'm supposed to turn my video off now so that I can concentrate. There we go. So it's made up of these two characters, tsu, meaning harbour, and nami, meaning wave. So the word tsunami really means harbour wave. So the reason the Japanese named it this way is because it's a wave that you really can only see in a harbour. If you're out at sea, as we'll see later, given that it's such a long wavelength and a small amplitude, you really don't notice it. So it can be in a boat in the open ocean, a tsunami can pass under you, you wouldn't even notice. But it's only when it gets to shore and it starts shoaling that it increases in amplitude, and then it becomes noticeable and it can have those impacts at the coast. So here's a little depiction of shoaling. So for a tsunami in the open ocean, just go to these polls and chat boxes here so you can see my cursor. For a tsunami, for a tsunami in the open ocean here, given that it's what we call a shallow water wave, the energy actually reaches all the way down to the bottom of the ocean. And as it moves, this is how I think of it anyway, and as it moves into shallower water, that same amount of energy needs to squeeze into a smaller depth, and so the amplitude of the wave increases. So that process of shoaling, when I say shoaling, it's just the fact that a wave increases in amplitude and steepness as it moves into shallow water. So a tsunami does this, and this is why you can't see it in the open ocean. You can only see it at the coast. So moving on to more the, so I should say that's why it's called that's why it's a harbour wave is a good name for it. Moving on to more of a formal definition, a tsunami is formally defined as a series of waves generated by the sudden displacement of a large volume of water. So usually we think of these as actually occurring in the ocean by an earthquake in the ocean, but actually you can step in a puddle and cause a tsunami, or you can drop something in your bathtub and you'll cause a tsunami because you've displaced water and that wave is propagated away from that area. But we're just talking about tsunamis in the ocean here, and the number of different kinds of phenomena that can cause that displacement. So we have underwater earthquakes, and I'll be talking a lot about that in the rest of the talk. You can also have landslides causing tsunamis. Now these can either be submarine, so underwater, and that could maybe be a bit of the continental shelf that has come loose and slumped, cause a tsunami, or it could be a sub-aerial landslide, and that's a bit of the land, maybe a cliffside or even an iceberg that has fallen into the water and caused a displacement. Volcanoes can also cause tsunamis. These are generally a similar kind of mechanism, in which case there's when there's a volcanic eruption and there's a flank collapse, that flank collapse falls into the water, causes a displacement and causes a tsunami. Asteroid impacts could potentially also cause a tsunami. Thankfully not one in my lifetime, and I don't expect there to be one. But there is a theory that it was an asteroid and a major tsunami and changes in the climate that wiped out the dinosaurs. And finally, there's these things called meteotsunamis you may have heard of, and these are actually caused by atmospheric pressure. So it's very different to things like a cold front or a tropical cyclone causing a storm surge. This is a sudden change in atmospheric pressure, which then causes a resonance effect and a tsunami propagating away from that region. So looking at the frequency of these different types of causes for tsunamis, most of them are caused by earthquakes. So 81% of the known tsunamis are caused by earthquakes. So for the rest of this talk, I'm really just going to be talking about earthquake-generated tsunamis. So we'll first look at where these earthquake-generated tsunamis occur. They generally occur on plate boundaries, and this is where the continental plates are moving around and bumping up against each other. So this figure shows, the red lines show the edges of the continental plates, and the black arrows show how they're moving around. So as they move around, of course, this is very slow, it's millimeters per year, but as they move around over time, there's friction between plates and stress can build up, and then once that stress is released, that's an earthquake. So I think we've got a little depiction, little animation of that happening here. So here we have two plates, this one moving in this direction, this one moving in this direction. At a particular point, that stress has built up and then suddenly releases, causing a displacement in the ocean surface, and then the tsunami to propagate away. So stress building up, released, causes a displacement, and then goes the tsunami. So this is a case where you can see this plate on the left is, they're moving towards each other, and this plate on the left is moving beneath the one on the right, so it's subducting beneath it. So this kind of boundary we call a subduction zone. So going back to our map of the plate boundary, we can actually look at this and see which ones of these are subduction zones, and so which ones of these are most likely to cause tsunamis if there's an earthquake. So for example, if you look at this little Philippine plate here, you can see the Pacific plate is moving in this direction, Philippine plate is moving in this direction. Philippine plate is actually subducting beneath the Pacific plate, so this is a subduction zone here. Interestingly, this one to the north of the Philippine plate is also a subduction zone because the Eurasian plate is moving faster than the Philippine plate, so this is subducting beneath the Eurasian plate as well. So you can sort of look at this and see where the subduction zones are. Of note, this one definitely is not a subduction zone because you've got the Australian plate moving away from the Antarctic plate. We can also see where the subduction zones are by looking at where earthquakes that have generated tsunamis have occurred. So if you look at this map, which is provided by our colleagues in the US at NOAA, each coloured circle or white circle shows the location of an earthquake that has generated a tsunami. So that also shows us where the subduction zones are. So you can see there's this, don't ask me what the names of these zones are. They all have names, but I never remember what they are. There's this zone in the Indian Ocean. I think that's the Sunda Arc, or part of it is the Sunda Arc. We've got this zone south of New Zealand and north of New Zealand, and then all around the Pacific Ocean, there are subduction zones. So this is often called the Ring of Fire because pretty much every boundary on the Pacific Ocean is a subduction zone apart from the south. So you can see no earthquakes generated to the south here, or no tsunami generated earthquakes to the south here, which is good. Okay, so moving on, we now know where tsunamis are generated, and we know how they're generated, and we know a little bit about fluid dynamics. So we can now create numerical models to model them. So what we've got here is, I've just set that going, is an animation of, I guess it's an animation of a numerical model of the 2004 Indian Ocean event, magnitude 9.1. And so we've, what we're looking at is the amplitude of the wave here. So we have crest, I might stop that here. The crest is white, so it's above mean sea level, and light blue is below mean sea level. So for a start, one of the things I would like to point out here is you can see this wave has quite a long wavelength. So the wavelength is the distance between two crests, or the distance between two troughs. And while that varies a lot over the map, generally it's going to be hundreds of kilometers long. I'll keep that going again. So the wavelength is hundreds of kilometers, but the wave amplitude is only tens of centimeters. So this is why it's very hard to see out in the open ocean. So because the wavelength is so long, this means that it's what we call a shallow water wave or a long wave, and it will actually feel the bottom of the ocean. So it knows how deep it is, and this means one of the features of shallow water waves is that the speed at which they travel is dictated completely by the depth of the ocean. It won't have anything to do with the size of the earthquake or the size of the wave or anything else. It's purely dependent on the depth of the ocean. So this means, I might just start that again so you can have a look at it. Start it again. So this means that if we know when an earthquake has occurred, one of the first things we can do is provide a reasonably good prediction of when the tsunami will arrive at the coast. So you can see I haven't got the depth of the ocean plotted here, but you can certainly see that to this area north of Australia around Darwin, it's slowing down, whereas it's hooning around the south here because this is deep water. So it's going to get to certainly Tasmania before it's even reached Darwin. So that's a reflection of the fact that the water is shallower north of Australia and deep south of Australia. So tsunamis are long waves. And another key important point is that it's because of their long wavelength that they can inundate areas of the coast. This is quite different to wind waves. Wind waves can be a lot higher than tsunamis. They can be meters high, tens of meters high in the open ocean. But because their wavelength is only tens of meters long, they can't actually inundate the coast. So it's really the long wavelength of the tsunami that allows it to inundate the coast, not its amplitude, although a higher wave will inundate further. So one thing to learn from today, at least, is that tsunamis are best described as long waves, not as big waves. All right, I might just take this back to the initial condition now so we can look at that. So as I said, white means a crest, light blue means a trough. So because of the dynamics of this earthquake here, and you can see it had quite a long rupture, it's not just a circle, it had a very long rupture. This means that the tsunami starts off with a crest going towards the west and a trough going towards the east, towards Malaysia and Indonesia. And because in the areas where a trough arrives first, that is actually, you'll see drawdown. You'll see the water retreating from the ocean, from the beach, before it actually inundates. And as you may have heard some stories about that happening in Indonesia, some people were able to see the water drawing back and realize that was a tsunami and managed to escape. But that doesn't always happen. It depends on which side of the subduction zone you're on. So there'll be drawback on the eastern side here, but the crest will arrive first, so there'll just be straight inundation on the western side. The other thing, I'll just set this going once more. The other thing which is nice to look at is some reflections and all sorts of constructive and destructive interference going on. But if you watch carefully, you might be able to see the wave reflecting off Sri Lanka as it arrives. So there you can see that wave coming back here. So you can see by the time a later wave arrives at Indonesia, it's going to be quite complex. And there's all sorts of other things you can see here. You can see some island blocking. You can see other areas where the bathymetry or the depth of the water has had some impact. You can see the wave coming up the New South Wales coast. I could look at that a number more times, but we have a webinar to get through, so we won't for the time being. Okay, so now we're looking at tsunami hazard. So we've done tsunami basics. We'll look at tsunami hazard for Australia. So historically, and I'm taking this information from this paper here, the Australian Tsunami Database, a review published in 2014. Historically, there have been 145 known tsunami events reported in Australia. And of those 145 events, 125 are from historical documents. So that's really since European settlement, and that's in newspapers or other written reports. So that's where we get our approximately one tsunami every 2 years is observable in Australia, because we've had 125 over just over 200 years. And then there's another 20 paleo tsunamis, and these are events which have been deduced from looking at geological deposits, and so knowing that there must have been a tsunami to be able to put that deposit there. Interestingly, the states, the regions that experience the most events are, we need to move that, just move that over. Where shall I move that? There. Queensland, New South Wales and Tasmania have experienced the most events, and that is because they're on a specific ring of fire where most earthquakes in the world actually occur, or most tsunami generating earthquakes occur. Of these events, of these 125 events, most of the impacts are fairly minor. Unusual currents in the foreshore, small amounts of inundation onto the foreshore, but mainly just unusual tidal currents. I'll just discuss a couple of recent events where we did see some perhaps non-negligible impacts, depending on your point of view, really. So firstly, with the 2004 event, this was, okay, so the event was here. That's where the source was that we saw in the previous animation. And just, did that disappear again? There. And just looking at what happened to that event, what happened during that event, we can see there was some minor impacts on Western Australian coast, although I guess if you're the owner of that boat, you don't think it's a minor impact. So here in Geraldton, you can see a boat sunk, and there were impacts like that. Another event where we saw some impacts was July 2006. This was magnitude 7.7 event earthquake near Java. So the source of the earthquake was here, and there was a campsite here at Steep Point in Shark Bay, where due to a lot of the local topography, there was some funneling, and this particular campsite saw some quite significant impacts. No one was hurt. They all managed to wake up and run away, but the campsite was destroyed. And this event, actually, this 2006 magnitude 7.7 event, does have the honour of being the event that has caused the greatest impact on the Australian coastline. So the biggest tsunami we've seen in 200 years. Okay, so that's what we have seen. In terms of what we might see, what I'm going to discuss here is some work that's been done by our colleagues at Geoscience Australia. So they've undertaken over the past several years a probabilistic tsunami hazard assessment. So this is based on what we know about where tsunamis are generated, subduction zones, their probability of occurring. So that's a lot of analysis about the earthquakes and about the plate tectonics, and then what we know about how tsunamis evolve as they propagate over the ocean. And from all that work, you pull it all together and we can come up with a probabilistic tsunami hazard. So what we're looking at here is essentially risk area. So it says a 1 in 1,000 year maximum amplitude of a potential tsunami. So I can see the highest risk along the Australian coast is in the northwest shelf, and that's essentially due to this subduction zone in Indonesia. The risk reduces a lot along the southern coast because we have no subduction zones in that area, and then Tassie and New South Wales have a little bit of a higher elevation. Earthquakes occur in the Pacific Ocean. So I just want to touch on what this 1 in 1,000 year maximum amplitude means. So what that doesn't mean, because you may have heard of it in terms of floods or storms. This is a 1 in 50 year storm. This is a 1 in 100 year storm. And the next year we have another 1 in 100 year storm. That's not necessarily a contradiction. So this 1 in 1,000 year maximum amplitude doesn't mean that it's going to happen exactly once every 1,000 years. So the way I like to think of it is that if we had 1,000 versions of Australia and we watched each of them for a year, then on average, one of them would have a highest tsunami as big as this wave, as big as depicted here. It may not actually be one. Actually, you'd need to do that experiment a number of times. So you'd need to have a number of instances where you watch 1,000 versions of Australia for a year. You pick a particular point on the coast. Maybe in some of them, you'd have 2 events of this size. Maybe in some of them, you'd have no event of this size. But on average, over 1,000 years, you'd experience one wave looking like that. So that's why happening twice in a row in 2 years isn't necessarily a contradiction. It's just statistics. Okay, I think we're going to hand over briefly to Jordan.
Yeah, we'll start our next poll. Thanks, Diana. Great to know, excuse me, a little bit more about tsunamis and how they're formed. And before we get the inside look at how we monitor for tsunamis, we're going to get to our second poll, as I mentioned. We'd like to know what is the minimum amount of warning time you'd receive for a tsunami anywhere on mainland Australia? And there is a little clarifier to that, isn't there?
Yes, we are talking about subductive zone earthquakes. So we're just talking about the earthquakes that we warn for, which are tsunamis generated by earthquakes that occur on subduction zones.
Okay, so the ones that she was just mentioning before, how much time do you think on mainland Australia the warning time you'd receive is? Is it A, 10 minutes, B, 30 minutes, C, 1 hour, or D, 1.5 hours? While we get those answers in, we've got some really great questions to get to. If you have a question, please put it in the chat after you've done your poll. We'd love to throw anything at Diana, see if we can stump her. I'm kidding, Diana.
Not everything.
John has asked, what areas does the tsunami warning system cover? And are some areas of Australia's coastline that are not covered by the system?
I believe I can categorically say that all areas of Australia are covered by the warning system. So that's, and I'll show the map later. So that's all mainland and all our offshore territories as well. So Cocos and Christmas Island in the Indian Ocean, Norfolk, Lord Howe, and a few others, Macquarie, maybe there's one more, and even our Antarctic territories as well. So we do provide tsunami warnings if needed for all those areas.
Okay. Ken has asked, although tsunamis occur from time to time, Australia seems largely unaffected. And we've kind of mentioned this in the previous part. Is this just a matter of good luck, or are we not quite in the right space?
Well, I think it's a bit of both, actually, a bit of column A, a bit of column B. I think predominantly, but we don't see the kind of impacts in Australia that we would in Indonesia or Japan or the US, because we're in the middle of a continental plate. So our subduction zones are all a little bit distant from us. So, and even the ones that are the closest ones potentially couldn't support a really large earthquake. So yeah, it's because of our position in relation to the subduction zones.
Okay. We've got a question from Ross, who's logged on today and wants to know, how does the rate of change of the depth of the sea floor affect a tsunami as it reaches land?
Well, I guess that's the shoaling that I talked about before. So that's essentially the amplitude grows as the water gets shallower. I mean, at a certain point, the wave will break, but not always. Sometimes you can get sort of hydraulic bores and all sorts of things. So yeah, there's a little rule of thumb equation where you can look at the height of the wave as a function of the depth, but I won't go into that now because it's an equation, and equations scare some people. Not most of us, but some people.
Yeah, definitely me as well. I have a question from Graham that's come up, and it's one of those questions that I've had to read twice, but as soon as I read it, I was like, that is an incredible question. So,
well, you might have to ask it to me twice then.
Okay. He said, Mr. Graham, excuse me, he's said he's enjoying the presentation so far, but he wants to know whether there's been a history of a collision of two tsunamis. So maybe two earthquakes made two tsunamis, they travel towards each other, and when they hit, are we looking at complete chaos or like square waves being produced and weird things coming out of it?
Yeah, so that's a good question. So I think I would think back to some of these really large events we've had, sort of the Japan event was magnitude 9 and the Boxing Day of magnitude 9. Often, while they were 10 years apart, often when there's a big earthquake, I think always actually you'll have aftershocks. Those aftershocks generally are not as big as that earthquake, but they can be still substantial. So for example, after the magnitude 9 event, you might have a magnitude 7.5 event maybe 6 hours later. And given that the tsunami from the earlier large event it can slosh around the world's oceans for more than 24 hours. So that's still going to be sloshing around by the time the aftershock comes. So that's certainly an instance where I think you'd have two occurring at the same time. You just have constructive interference and destructive interference. We saw a little bit about that in the animation. I do not know what would happen if you had two magnitude 9 events occurring near each other. That would be interesting. But I can assure you that the Australian Tsunami Warning System would be well set up to be able to warn of any potential impact.
So it's kind of like that, the irresistible force meets the unmovable force, or whatever that saying is.
Well, to be honest, they may just pass through each other, So the waves, it's just the energy propagating on the ocean surface. So they'll just pass through each other. Maybe there'll be a bit of, interference and a bit of slowing down, but I think they just happily propagate.
That's interesting. I didn't know that they could pass through each other. That's super interesting. Yeah, we're going to get to one more question and then we'll finish off our poll, but there is time for plenty more questions, so keep sending them in. We love to hear them. Ben has asked, and I think we answered this a little bit, but his second part's really interesting. What do you think are the key triggers or risks for the East Coast? Where is the meteor tsunami risk highest in Australia? And like I said, I think we've answered that a little bit with that map, but his second part is, how is tsunami risk considered in infrastructure planning? If you have anything to answer on that, I would find that really interesting.
Yeah, so that's a good question. I don't do infrastructure planning myself. If I did, I would be taking risk into account. So you'd really need to look at the planners. I know that there's certainly some guidelines for doing hazard assessment for particular infrastructures. So when ports and harbours are built, certainly many groups will take that into account. What was the question specifically?
Well, at the start of the question, and I know it was a two-parter, so I'm sorry. They wanted to know, what do you think are the key tsunami triggers or risks for the East Coast, and where is the meteor tsunami risk highest in Australia?
Okay, so that's two questions as well.
Yeah.
So the highest risk for the East Coast, to be honest, I'd refer people to the probabilistic tsunami hazard assessment for that, and I'll provide a link to that at the end of this talk. But certainly we've got subduction zones off in the Pacific Ocean which provide the risk for the East Coast. The other ones are specifically about meteo tsunamis.
Yes.
So, that's kind of a new area of research, and I know there's been a lot observed in Western Australia, some in Bass Strait, but often we just haven't found them all, So I think a good Google would probably give you the answer to that.
Okay, we do have time for questions a little bit later on, but we want to keep going into the webinar now. So we'll just put a pin in that for right now. We do have our answers from our poll, and the overriding answer is B, 30 minutes. They believe that you'd get 30 minutes of warning time. What's the answer?
Well, I'm pleased to say that we would probably provide 1.5 hours. Well, not probably, we will always provide at least 1.5 hours of warning for a tsunami from a subduction zone earthquake anywhere on mainland Australia. And the reason we know that is, or the reason we can provide 1.5 hours is if we look back to our map of the earthquakes that have generated tsunamis, the closest subduction zone to Australia, or the closest source and impact point, is actually south of New Zealand, the Paisega subduction zone. Potentially, with if a tsunami was generated in that area, it would take about 2 hours to get to Tassie, and that's the quickest, that's the shortest time that any tsunami would take to get to Australia. Interestingly, this subduction zone north of Australia, while it's geographically or physically a lot closer, because this water is so shallow, the tsunami takes a long time to get there. It actually takes about 8 hours to propagate across the Timor Sea, the Timor-Arafura Sea here. So this is our shortest zone. We know that we can issue a warning within half an hour of the earthquake, and so that's what gives us at least 1.5 hours of warning time. You'd get more for areas further away, you'd get more warning time, or for earthquakes further away, you'd get more warning time, but it's always going to be at least 1.5 hours.
Oh, wow. That's very impressive. 1.5 hours is fantastic. So our final Q&A session is going to come up in just a little bit. So we'll get to more of your questions then. Right now, Diana's going to spend about 15 minutes or so talking a little bit more about the observation system that the Bureau has.
Yep. Okay. Thanks, Jordan. Second half of the talk. All right. So we have two main instruments for observing tsunamis. And when I'm talking about observing tsunamis in this case, I'm really talking about sea level. So we're talking about variability in the sea level. So we have tide gauges and tsunameters. Tsunameters is often called darts, but that's actually that's the brand name. So it's like calling a vacuum cleaner a Hoover. So I'll try and stick to tsunameters rather than darts. So the advantage of tide gauges is they're relatively cheap to install. There's lots of them around. So they've been around certainly before 2004. The disadvantage is they're generally in ports and harbours, so you don't see the open ocean variability of the tsunami. And often by the time the tsunami has arrived at the port or a harbour, it's sort of too late to be able to get that information into the warning system. So it's useful for verification rather than warning. On the other hand, tsunameters are very flexible. You can locate them anywhere in deep water. That means you can put them near subduction zones where you can get an observation of the tsunami soon after it's generated. The drawback to them, though, is they're very expensive to maintain, because in the open ocean, you need to hire a ship, you need to get out there, you need to get something that can drop 5 kilometres down in the open ocean. This map on the right actually shows, this is a snapshot of the real-time display that our forecasters have access to in the operational centre. And this shows the various, a subset of sea level stations that they can have access to. So in the operational centre, they can click on one of these coloured diamonds or circles, and that will bring up the display of the sea level in real time. What you probably can't see, circles are tide gauges, diamonds are tsunameters, but I'll be showing those a little later. Also, what you can see is the red ones are the ones that are not operating, and the green ones are the ones which are operating, and I will talk about that a little bit later as well. Thankfully, all these ones around Australia are working quite well. All right, so first we'll look at tide gauges. This is an approximate, the top map of approximate location of the tide gauges which report to the Bureau in real time. So in order for a tide gauge to be good for warning, it's got to firstly report, or warning or verification for that matter, reporting in real time, so that the Bureau gets the data as soon as it's observed the tsunami. And also it needs to be recording frequently. So watching the sea level, recording every minute or so. There's a number of different ways that tide gauges can measure tsunamis. So we have acoustic tide gauges, such as in the bottom left here. So there'll be an acoustic sensor just here. There's a tube which sits at the end of a jetty. This acoustic sensor tends to ping down to the ocean surface, and then knowing how fast it goes and how long it takes to get down and back, it knows the height of the sea level, so it can know the height of the tide or the tsunami. There's also radars which work in a similar way, and pressure sensors as well. I feel I'm going to have to zip through this a bit quickly. Here's some examples of the type of signals that tide gauges can observe. So these are examples during the Japan tsunami in March 2011. This top one is from an island, Papua New Guinea here, and this bottom one is at Port Kembla, so inside a harbour. You can see the wave's quite different. So key point from this is that the first wave is not necessarily the biggest. In fact, it's barely the biggest. And in this case, it's arrived about 4 hours after the first tsunami's arrived. Same goes for the Port Kembla case. The first wave is certainly not the biggest. Another point to notice is that the frequency of the waves in these two locations is quite different. So in this northern one, we've got a nice clean signal. So the earthquake source, it's not shown on this map, but it was to the north and pretty much had a direct route straight down to this tide gauge here. So you've got a nice clean wave arriving, whereas by the time it gets to Port Kembla, it's had to propagate through all these island chains and a lot of shallow water, and what's more, this is inside a harbour, so you've got a lot of sloshing and sashing going around. So the frequency is a lot higher and it's a lot messier signal. Okay, so that's tide gauges. Now moving on to tsunameters. We've got a little depiction here of how the tsunameter works. Essentially, it has 3 parts. This bit on the right is just the same thing, but with a bit more detail. There's a surface buoy, which does the communications back to the warning center. That has an anchor as well to keep it in place. And then there's the tsunameter, or the bottom pressure sensor, which actually does the measuring of the sea level. And what that does is when there's an earthquake, that triggers a tsunami into action. It starts recording more frequently. And because the seismic wave travels faster than the tsunami, it'll be triggered into action before the tsunami gets there. That detects the change in pressure, which it then sends back to the warning center via satellite. So what I find amazing about these things is that this change in pressure, which is then converted to a height, it can measure that height. It can measure the change in height to an accuracy of about 1 millimeter, and this is 5,000 meters of water. So I think that's actually quite amazing, and they are extraordinarily valuable for tsunami warning purposes. So here's a global map of where all the tsunameters are at the moment. So this global network is made up of a number of different national networks. The US certainly has the largest number of tsunameters, but there's also Japan, Indonesia, Chile, India that have quite a few, and Australia as well. So we have 6. These are owned and operated by the Bureau of Meteorology, funded by the federal government, and we've deployed them in 3 lots of pairs. So the reason we've done this is a little bit for redundancy. You can see, because they are expensive to maintain, if one goes out, it can be months before you can get a ship organized to actually go out and fix it. And so we've done this a little bit for redundancy. If one of them goes out, then there'll still be another one there to warn us. And so these are placed essentially between subduction zones and the Australian coastline. Interestingly, before 2004, there were only about 6 of these in the world's oceans, and they were sort of experimental instruments in the North Pacific. After 2004, the world came together and said, okay, we clearly need an international tsunami warning system, so a lot more were deployed. And today there's actually 63, if you count these up, there's 63 in the around the world's oceans. Interestingly, there's a bit of a gap here to the north of New Zealand, in the Southwest Pacific Ocean. The US used to have some, but it was just, it's their priority is to maintain the ones closest to them. Luckily, New Zealand has now come to the party, and they are in the process of deploying 12 tsunameters, definitely punching above their weight. And so they're going to be in these locations here. So once these are all deployed, there'll be a global network, excuse me, of 75 tsunameters. And here's just a depiction of what a tsunami signal looks like. When there's no tsunami, they will sit quite happily on the bottom of the ocean recording tides at every 15-minute intervals. So there's enough that's quite interesting in looking at tidal signals. When an earthquake comes along, the seismic wave will trigger the tsunameter. You can see that's what these red lines are. That is actually the seismic earthquake. So it's not a change in sea level. It's just the bottom pressure sensor being jolted. Triggers into action, and then it'll start recording more frequently at 15 seconds, and then the tsunami comes along here. So you can see this is the Japan event 2011, the tsunami coming along here, and this is another event a little earlier. Same kind of thing happens, but you can see a much smaller tsunami. But you need to be careful that you don't interpret the red lines as the tsunami. That's just the earthquake. Okay, so last section, now moving on to tsunami warnings for Australia. So tsunami warnings are issued by the Joint Australian Tsunami Warning Centre. This is a joint centre. Well, the reason it's called joint is because it's operated jointly by Geoscience Australia and the Bureau of Meteorology. It was established after the Indian Ocean tsunami of 2004. So the way it works is when there is a seismic event, i.e. an earthquake, Geoscience Australia have their network of seismometers and also international collaboration, and they will detect that earthquake and analyse it, and then if it is potentially tsunamigenic, the Tsunami Warning Centre will be triggered into action and they will start talking to us here at the Bureau. So by potentially tsunamigenic, that first has to occur underwater. So if there's an earthquake in the middle of Siberia, for example, however big it was, unlikely to cause a tsunami, so they probably wouldn't bother us. And it needs to be magnitude at least 6.5. So that's a little conservative. To be honest, I don't get out of bed unless it's at least a magnitude 7. But this is a formal requirement for the earthquake to be potentially tsunamigenic, i.e. causing a tsunami. So then the Bureau will look at our sea level observations to see if there has been a tsunami generated. We'll determine impacts, and I'll talk about that a little later if we've got time, forecast the wave arrival times, and then issue the warning if necessary, or issue a no threat. And then the rest of this diagram shows the various communication channels, which I won't go into, but you can certainly find more information of that on our website. So the tsunami warnings, you can find them on the Bureau's website. So if you go to the bom.gov.au, which I assume people know about, under the drop-down menu on the right-hand side under Warning Services, there's a Tsunami Warning System button or tab. You click on that, and most of the time you will see something which looks like this: no tsunami currently affecting Australia. Phew. And then if you need more information on the right-hand side, there's bulletins. Actually, there was one this morning, so it may not be saying that at the moment. 10:30, there was I think a magnitude 6 in the Philippines, 6.5 in the Philippines. So it may not actually look like that now. What it may look like is this, for example. So this was actually 2 weeks ago when I first started putting this talk together. On the 5th of August, there was a magnitude 6.5 event near Vanuatu. So this is what the site would look like. There'd be, this is for no threat to Australia. There's no threats for all of our mainland coastal zones and all these offshore zones as well. It shows you the location of the earthquake, or if it's not in this map, there'll be a little inset. And then you can click on the National Tsunami Bulletin here, and you'll get this extra information here. So this tells you where the earthquake was, what magnitude it was, latitude, longitude, and no tsunami threat to the Australian mainland, islands, or territories, which is good news. Now, in the event that we would need to issue a tsunami warning, we do have 2 different levels of threat. So the tsunami watch is something that's, if it's potentially going to cause an impact, that'll be issued rapidly while the threat level is assessed. And then we have these 2 levels of threats. We have a marine threat and a land threat. So for this example here, we've got these 2 zones in blue will potentially be under a marine threat, and the red a land threat. So what that means is, for a marine threat, we would expect impacts really just in the marine environment. So dangerous rips, waves, currents, and some localized overflow onto the immediate foreshore. Advice to get out of the water and move away from the immediate water's edge, but we don't expect any major inundation. That would be, if we did expect major inundation, we would issue a land threat, and that would be for major land inundation, flooding, also all these impacts in the water. And people in affected areas are advised to go to higher ground or at least 1 kilometre inland. So this is what would be in the National Threat Bulletin. Obviously, these are issued for individual zones. So the threat level will be defined for those individual zones which we saw. Now, how do we determine what level of warning to issue? Well, so we've talked a little about earthquakes. Obviously, we can't predict earthquakes, so we don't know when a tsunami will occur, but we do know where they're likely to be generated, and that is along subduction zones. Now, generally, at least at the time when we were setting this up, the time between the earthquake, i.e. the tsunami generation, and a potential impact on the coast is too short to be able to model it in real time. So we don't have 3 to 5 days lead time like we might for a cold front or a hailstorm or a tropical cyclone. We've got, 2 hours at most. So what we do is we have pre-computed any tsunami that we think might impact on Australia that is generated by a subductive zone earthquake. And then when that earthquake occurs, we can just pull it out and we have our forecast. So we call that, we've got a pre-computed tsunami scenario database that covers all the potential impacts that we think we might see. This is a couple of examples of what I would think of as a scenario. So this is an example that represents the Japan magnitude 9.1 event of 2011. So what we have here is the maximum amplitude at any point. So recall the animation that we saw before. You just sit at a particular point, and over the 24 hours of that animation, or 48 hours, or whatever it is, you record the maximum wave amplitude that you've observed, and then plot it all up, and it looks like this. Obviously, it's higher close to the event. It gets less as you go further away. You can see these patterns here, which some people call the fingers of God, which are a function of blocking by islands and little shallow waters where we're seeing shoaling. So what we do is we look at this scenario and we look at the Australian coastline. You can see the shoaling has occurred here. And we look at what the wave amplitudes are in that area. There's another example here of a scenario. I like showing this one because it's a hypothetical event south of in the southeastern Pacific. But what it shows is that New Zealand very kindly blocked a lot of the energy from arriving at the Australian coast. So that's another big thank you to New Zealand for that. So this is another scenario here, an example near Java. In each of these coastal zones, we look at the maximum amplitude that's occurred. If it meets a particular threshold, we'd issue a marine threat. If it reaches a higher threshold, we'd issue a land threat. So combined with all the observations that we see, that is how we would determine the level of warning. Okay, so what to do if you have heard there's an earthquake or you've heard there's a tsunami? So generally mass media, i.e. TV and radio, will disseminate the key warning messages coming from the Bureau. We strongly recommend that you check the Joint Australian Tsunami Warning Centre webpage for the most authoritative information. There's other groups around. For example, the US will sometimes try and issue a warning for Australia, but we would say that the JATWC is the most authoritative warnings. Then depending on what state you're in, sort of state or territory emergency services may send SMS messages if you're in a particular threatened community. I know I certainly received one for a bushfire alert a couple of years ago, even though I'm in the middle of Melbourne. So that was both reassuring and alarming. If you're at the beach, for example, at the coast, then local authorities will come and close the beaches if there's a major threat. They'll come and move you away from the coast. And you can always call 1300 tsunami if you like. Finally, I'll just point to these signs here. We don't have tsunami evacuation routes like indicated here, and that's because we always know we've got at least 1.5 hours to be able to issue a warning and to be able to communicate those warnings to the people who are at threat. That is not the case for all countries where they're right on a subduction zone, and they may only have 15 minutes between the earthquake and the tsunami arriving at the coast. So in those cases, if you're on holiday, for example, the recommended action is if you're near the beach and you feel an earthquake, then just move away from the water. So these are some example signs of tsunami evacuation routes to follow. This orange one is Indonesia. This one on the right is USA. Bottom right is Chile, and potentially confusing next to the street line. Just make sure you follow the green arrow, not the black arrow. And then this one here is in Japan. So I think that is all I have of the formal part of the webinar. Back to Jordan.
Yeah, great. We are running a little bit behind time, so we're going to try and get to as many questions as we can. So I apologise for everybody who was planning on leaving it at 2, but we will have a little bit of question and answer time now, because I know a lot of people are interested in getting their questions answered. Lance has asked, wouldn't the size of the tsunami depend on the volume of water displaced and not the earthquake's magnitude?
Well, that is an excellent question. And yes, it does depend on the volume of water displaced, and that is generally dependent on the earthquake magnitude. But of course, you can have an earthquake magnitude that doesn't have that uplift, in which case it won't displace the volume of water. So yes, when I'm talking about the earthquake magnitude having an impact on the tsunami size, I'm assuming that it's an earthquake that has that uplift.
Okay.
It's a good question.
Patricia's asked a really interesting one that I didn't even think of. Is there a monitoring of conditions of the continental shelf around Australia to determine the likelihood of a tsunami that was generated by like a chunk of the shelf falling off?
Oh, that's a good question. So landslides, tsunamis are very difficult to warn for, and this does come up occasionally. There's certainly some research going on into landslide areas. I think the best we can do is just be aware of where the highest hazard is. I think being able to provide a warning for those landslide tsunamis is a long way away yet.
Okay. So, I believe you answered it a little bit more, but Zachary wanted to find out just with the SMSs being sent out to areas under threat, that would just be automatic, right? We would all get those depending on where we are, like location based.
Yeah, to be honest, I can't really answer that one because it's not really my area. But we can look into that and provide information afterwards. I'm not on the operational warning side, I'm afraid. So
Yeah.
yeah.
And I think you might have answered this as well because Mike has asked, do landslide induced tsunamis represent a higher risk than earthquake induced ones?
Again, good question. I think that's an area of active research, so we can't really answer it now. But I would suggest that given the frequency of landslide tsunamis is a lot lower, we just don't experience them as often, then the earthquake generated tsunamis are probably a higher risk at this stage.
Ross has sent us something that says, do tsunamis trigger for other than earthquake tsunamis, like through the pressure of...
Yes.
They do?
Well, I think they do, yeah. So sometimes they just trigger randomly. Who knows what's going on down at the bottom of the ocean? You know, maybe a fish has bumped into it or something. There potentially, I don't know, some atmospheric phenomena, although I don't really think how that can happen. But certainly, I mean, they can be actively triggered as well. So, you know, the operators would go and test them every so often. They'd send a trigger just to make sure it's working. But yeah, they can certainly be triggered for reasons that are unknown.
Okay. This is fast, rapid questions because we've got a lot. Ashley, they've asked, what is the largest tsunami ever recorded in Australia, like to impact mainland Australia, excuse me, particularly during the Pleo timescale? I hope I've said that correctly.
Yeah, paleo.
Paleo, sorry.
Okay, yeah, that is not my area, and I would probably refer you to that paper by Goff and Che Goff which looks at the Australian Tsunami Database. Unfortunately, I do not know that paper off by heart. Probably in there they would talk about the biggest tsunami to impact on Australia, but yeah, I can't answer that, I'm afraid.
Okay. Gary has asked, wave reflections appear to damage coastlines on the opposite side of land masses. Is there a lot of energy lost in the reflections, or can the waves become amplified and cause increased damage?
Good question. Yeah, so certainly a wave will lose some of its energy as it reflects off, in the case of a tsunami, off the continental shelf. I guess then they can be constructive interference as they propagate, but you'd expect the longer a tsunami's been propagating around and reflecting, the less energy it's gonna have.
Okay. So Vic has asked, does BOM require emergency services and broadcasters to convey the warnings to the populace at large beyond the tsunami warning system or page or hotline?
Yeah, I believe so. I think it's the job of the bureau is not. I think that's certainly downstream warnings, but again, not really my area. So we really should have had someone come in from the services side to be able to answer that sort of question. Yeah.
Okay. So, we've also got a question about geoscience from David. He's asked, does the geoscience analysis cover local effects as well?
That is a very good question. I believe they're actively working on that. So that hazard assessment that I showed you was actually at a particular area offshore. So that's a very good point in that provides us with what the highest expected or the 1 in 10,000 year amplitude is offshore. Local effects are going to be very important. And I know that actually there's a lot of groups that for example, a local council or a state will take that information from Geoscience Australia and do their own modelling and do their own assessment to see where the local impacts are greater.
Okay.
Yeah.
Excellent. Well, we're going to do our last question now because we are running out of time. Gregory has asked, the geoscience shows amplitude at the continental shelf. It would be quiet as it approaches the shoreline. And as the shelf seems to be very wide in the northwest of Australia, would this make the onshore hazard less?
Yeah, that's essentially what I just said. Yeah, so that is at the coastal shelf, and there does need to be that modelling to bring that onshore. That's
Okay.
right.
Fantastic. Well, thank you everybody for getting in your questions. We really appreciated them. If you didn't get yours answered, or if you have one that just pops into your brain, you're in the shower or something, you can send it to weatherquestions@bom.gov.au. But obviously, wait till you get out of the shower. A lot of information to take in there, but if you missed the start, Diana, would you mind summarising what we spoke about today and where people can find more information?
Sure. Okay. So just a few key points from what I've talked about today. Most tsunamis are generated by underwater earthquakes on subduction zones. Where's my cursor? Tsunamis, one key point is that tsunamis are long waves, not necessarily big waves, and it's their wavelength that causes the impact, not necessarily the amplitude. From the Australian Tsunami Database, we can say there have been 125 tsunami events recorded in Australia since European settlement, and most of these have had fairly minor impacts. And tsunami warnings are issued by the Joint Australian Tsunami Warning Centre. We have 2 levels of threat, a marine threat and a land threat, and a no threat, which is what most of them are. Here's some links for further information. So I've already showed the Joint Australian Tsunami Warning Centre, bom.gov.au/tsunami, or you can go straight through the Bureau's website, and that both has the official warnings and it has a whole bunch of more information. If you'd like to know more about the probabilistic tsunami hazard assessment, this page on Geoscience Australia has a lot of information about that, and you can also see another webinar, if you haven't had enough, by my colleague Gareth. Tsunami the Ultimate Guide is also an excellent site. It covers a lot of most of the information that I've talked about today, but in a lot more detail. So there's some really good slides there. And if you have any further questions, you can send them to weatherquestions@bom.gov.au. And if you say you attended the tsunami webinar, they will get through to the right place.
Excellent. And also, if you're struggling to scribble down those those links, they will be provided in a PDF when we send out the video on demand later on today, hopefully. So our next BOM webinar will focus on our next season. So even though it may be cold where you are right now, it's time to start planning. Spring 2020 Climate and Water Update will be on the 3rd of September. The change of season webinars are our most popular, and we put a lot of effort into them so you can make the right decisions for the months ahead. If you'd like to come along, then please click the registration link that is in the chat now so you can join us. And just a quick reminder that the Bureau has updated the app, its app, to provide a more detailed look at the weather where you are. There is no better place to keep up to date with everything that's happening than the official app. Grab it in the App Store or Google Play now. Well, that brings us to the end of today's webinars. Again, for any questions we didn't get to, please email weatherquestions@bom.gov.au. A big thank you to Diana for your time in developing the content and sharing your knowledge with us. And to you, thank you for tuning in and joining us today. We hope you enjoyed the session, and we do hope you'll join us again next time. If you'd like to continue the conversation, please use the hashtag BobWebinars in your LinkedIn posts. As mentioned earlier, this session has been recorded, and we will have the video for your on-demand viewing pleasure in the next couple of days, so watch this space. And finally, but most importantly, we want your feedback. It is our aim to bring you the highest possible quality webinar, but we can't do that unless you share your experience with us. Once we close this webinar, a short survey will pop up on the screen, and we'd be grateful if you could complete that anonymously for us. Once again, thank you for your time, and we look forward to seeing you again soon. Goodbye.
Bye.